In this video, we want to talk about electron configuration. Okay? We have talked about the principal energy levels. Atoms have a series of energy levels which are designated by these whole numbers. The energy of the level increases as the value of n increases, and as n increases, the energy level is farther away from the nucleus. So we had used rough pictures on the board of a nucleus here, and the energy level that was closest to the nucleus was n equals 1. Energy level that was next, farther out from the nucleus, had n equals 2, and so on. And as you moved away from the nucleus, the energy of the level increased, and the number we give it increases. So 1, 2, 3, and so on. Each of these principal energy levels has more than one subshell, where the number of subshells is equal to its principal energy level. Let's move on. Let's talk about valence electrons. By definition, those are the electrons in the outermost shell of the atom, outermost orbital, outermost principal energy level of an atom, okay? Core electrons are the inner electrons. And the orbital's definition is it's a representation of the space occupied by an electron in an atom, or the probability distribution for the electron. We said it's the space where there is a high probability of finding that electron. We are going to talk about this in a minute, but atoms of elements in the same group, which is a column of the periodic table, have the same number of valence electrons and the same number of electrons in a given type of orbital. We had talked before that the periodic table was set up and it put together elements that had same chemical characteristics, same chemical behavior, and those are arranged in these columns or groups. We'll show you why in a minute. We briefly discussed the octet rule. The octet rule is that atoms want to fill their outermost shell with 8 electrons, hence the word octet. So they're filling their s and p orbitals to try to get 8 electrons. And this octet rule mostly works best on the low atomic weight elements, the first 20, but it does help us explain why different elements will bond. All right, let's talk about sublevels. Here are our principal energy levels, designated by N. This also tells me how many sublevels it has. So principal energy level 1 has 1 sublevel, it's an S. Principal energy level 2 has 2 sublevels, S and a P. Principal energy level 3 has 3 sublevels, S, P, D. Notice we write the designation as the principal energy level number and the specific orbital we're talking about. So 2s, 2p, 3s, and so on. The numbers here after these orbitals, after these sublevels, tell you how many orbitals there are. So in an s orbital in general, an s sublevel, excuse me, there's 1 orbital, which can hold 2 electrons of opposite spin. A p sublevel has 3 orbitals. Each of those can hold 2 electrons of opposite spins. So a p sublevel can hold 6 electrons. A d sublevel has 5 orbitals and it can hold 10 electrons. An f sublevel has 7 orbitals and can hold 14 electrons. This is the chart from the PowerPoint that was very useful. It summarizes these first 4 principal energy levels. I'm kind of repeating some of these things, right? When n is 1, we have 1 subshell S. That subshell S has 1 orbital that can hold 2 electrons. Whoops. Sorry about that. Principal energy level 2 has 2 subshells. S has 1 orbital, P has 3 for a total of 4, each of which, can hold 8 electrons. Each of which can hold 2 for a total of 8, and so on. Here is a recap. We have sublevels. The sublevels are equal to the designation of the principal energy level. The first sublevel is always S. If you have 2 sublevels, you have an S and a P. If you have 3 sublevels, you have an S, P, D. And if you have 4 sublevels, you have S, P, D, and F. Okay? This was a very useful table that we handed out in class that helps us when we try to write electron configurations for different atoms. We are going to read this chart like we read a book, from left to right, starting at the top left corner. Let's say I want to write an electron configuration for oxygen, which has 8 electrons. We always said the ground state is the most comfortable state for an electron. But what we're going to find as our number of electrons increases is our ground state will be full and we'll have to move to the next energy level farther away from the nucleus, and so on. So if I have 8 electrons for oxygen, let's try to figure out where they will be. Well, we start here. The first 2 electrons will be in the 1s orbital. And guess what? Now 1s, the first principal energy level, is full. So we come back to 2 now. We're in period 2 on the table. We are going to fill 2s with 2 electrons. Keep moving along. And we've used 4 so far, so I have 4 more electrons. Well, I'll have 1, 2, 3, 4. We'll have 4 of them in the 2p subshell. 2p4. That is my electron configuration for oxygen. Okay? Let's try another one. Let's say we want to do, let's pick rubidium, which has 37 electrons. Now rubidium sits right here on the periodic table. So we're going to find that we have to work through period 1, 2, 3, 4 into period 5. Rubidium has so many electrons that it will have an electron sitting in the 5th principal energy level. Okay? So let's start by starting up at the top left corner. 2 electrons will fill 1s2. Now we're at period 2. 2 more electrons will fill 2s2. And then 2p will be filled with 6 electrons. Now I'm back to the 3rd principal energy level. 3s will hold 2 electrons. 3p will hold 6. So far I'm at 12, 14, 16, 18 electrons. I have several more to go. So I'm going to come down to period 4. Well, 4s will hold 2. But notice now I'm into the d's. This level of the d is always, the principal energy level of d is always the period number minus 1. So we're into the 3d's, and it can hold 10. And then I'm back to the 4p's, which can hold 6. I should have almost all of them, not all of them, but 2, 4, 10, 12, 18, 20, 36. I have 36. Go to period 5 now. My remaining electron will be 5s, will sit in the 5s subshell orbital. Okay, so there's the electron configuration of rubidium. Let's try another one. Let's pick sulfur. Sulfur has 16 electrons. So we're starting at the top right corner, top left corner, excuse me. 1s will hold 2, 2s will hold 2, and then 2p will hold 6. So I've used 10 so far. 3s will hold 2, and then I have 2, 4, 10, 12. I have 4 left. 3p will hold 4 electrons. Okay? Sulfur sits right here on the periodic table. Now, we know by the octet rule that these elements, or these atoms, would like to have a full valence shell or full outer shell. Well, sulfur's outer shell is 3, and it only has 6 valence electrons, doesn't it? So it will want to bond somehow so that it can pick up an extra 2 and be full at 8. But right now it has 6 valence electrons. The electrons, the inner electrons, which are called core, we have 6, 8, 10. We have 10 core electrons. Okay? So when we ask you how many valence electrons an atom has and how many core electrons an atom has, that's what we're asking. Okay? Let me back up to oxygen. Let's look at oxygen here. Oxygen's outer shell, its outermost shell, is the principal energy level 2. And in that principal energy level 2, it has 6 electrons. It has 6 valence electrons. And it has 2 core electrons. Okay? If we, for instance, take one of our noble gases, and let's take argon, which sits right here. So argon has 18 electrons. So let's see what its configuration looks like. Again, you would start at the top left corner. Well, 1s will hold 2. Now I'm into period 2. 2s will hold 2. 2p will hold 6. So far as I've used 10 electrons. 3s will hold 2. 3p will hold 6. Guess what? 2, 4, 10, 12, 18. I've used 18 electrons. That's the number of electrons argon has. Its outermost shell is the third principal energy level. Guess what? It has 8 valence electrons. It only wants 8 valence electrons. All the noble gases in this group 8 have 8 valence electrons. That, because they have all the valence electrons they want, they do not need to bond with any other atoms to gain or give up electrons. That's why they are very non-reactive. We call that stable, very stable. They won't react because they already have all the valence electrons they need. I'm going to move ahead to here. On a periodic table, if you kind of overlay the periodic table we had, we said, well, look, these are my s electrons. These are my p electrons. These are my d's, and these are my f's. Well, group 1 here has 1 s electron, 1 electron in its outer shell. It will have very similar chemical characteristics because it has the same number of valence electrons. They might be in different principal energy levels, but that's okay. So if you look at lithium, for instance, it has a 2s1 as its final part of its electron configuration. Sodium has a 3s1. Potassium has a 4s1. Because they have that 1 electron, 1 valence electron, they will have similar chemical characteristics. If you looked in group 2, okay, beryllium, it has a 2s2.